All right, chapter 12 talks about infrared spectroscopy and mass spectrometry. We're not going to be covering the mass spec. We will be talking about infrared only. There are tools that we could utilize in organic chemistry. IR is one of them. So infrared, it serves as a powerful tool to find out what functional groups we have in a chemical structure, while mass spec serves as basically giving us the molecular weight of it. NMR, which is considered the most important tool, it gives us the exact connectivity within a chemical structure, where the hydrogens are, where the carbons, how are they are connected, and the entire compound, how it's really connected. So this is a very important tool that we're going to go over in the following week, in the following lecture. Ultraviolet spectroscopy, that's basically for diene compounds and sometimes alkenes as well. So those are the tools that we usually utilize in organic chemistry for the purpose of analyzing compounds. So infrared. So when we look at the electromagnetic spectrum, we see one of the radiation type is IR. So infrared, it's a very strong energy that if we input it in a chemical structure, it will cause vibrations. And those vibrations that we're gonna see on the spectrum will be basically red and reciprocal centimeter unit. So if you look at this spectrum, you see a couple things. You see the wave number and you see the wavelength. We're not going to be using wavelength. What we're going to use, wave number. So the unit will be reciprocal centimeter. And the area of the IR, it usually goes from 600 reciprocal centimeter all the way to 4,000 reciprocal centimeter. And in this area, there is what we call the fingerprint region. This fingerprint region, which goes from 600 to 1,400, this is an area that we usually ignore. Why? Because there is going to be an overlap of peaks that are, it's going to make that region useless, that we're going to go through those peaks that's going to overlap. So that's why most of the time to analyze an IR spectrum, we focus on the area of 1,400 and above. And most of the peaks that we're going to need to figure out the chemical structure, what functional groups there are actually available within this region. Okay, two things I want to make sure that I highlight here as factors that we're going to find when we look at these numbers that we're going to have for those compounds. The first factor, the bigger the mass, the more energy is going to need for that compound to absorb, to vibrate. So if I have a C triple bond C versus a C triple bond N, so the fact that you're going to have a nitrogen that's going to be bigger in size or as an atom, that means it's going to require more energy to absorb. And that's why you will see that the C triple bond N absorbs at a higher frequency than the C triple bond N. So just keep that in mind. Also, when it comes to the bonds, the single bond versus double bond versus triple bond, the shorter the bond, the more energy is going to absorb. So that's something you're going to also notice within these readings that we're going to go over. A lot of chemical compounds we're going to visit. We're going to look at each category and find out the most important frequencies that we're going to have to be aware of. So let's start with hydrocarbons. Hydrocarbons, where we may have C single bond C, C double bond C, or C triple bond C. The C single bond C, as you notice, is 1,200, and it's within the fingerprint region. So right away, you could tell that it's actually useless to look for a C single bond C. However, the C double bond C will be around 1,600 reciprocal centimeter, while the C triple bond C is going to be about 2,200. So this is important to keep in mind. Now, along with this, keep in mind also the more conjugated, meaning when you have two double bonds, two double bonds separated by a sigma bond, like this structure, for example. You could see here that the absorbance will become 1620 versus the isolated C double bond C will be 1645. So having p orbital overlap within those double bonds will actually lower the amount of energy that's going to be absorbed. So just keep that in mind. That's why you see the aromatic, when you have a benzene containing compound, it drops all the way down to 1600 reciprocal centimeter. So that's an important trend to keep in mind. So for hydrocarbons, not only the C-C bonding we look for, also the hydrogens attached to them. So if you look at a C single bond CH versus a C double bond CH versus a C triple bond CH, it's easily can be detected what type of compound you have among those three categories. So alkane versus alkene versus alkyne. We already seen that the C double bond C reads around 1600 and the C triple bond C reads around 2200. But there is also another way to confirm this, the hydrogen attached to those functional groups. Hydrogen attached to a C single bond C will absorb less than 3000 reciprocal centimeter, versus the C double bond C will be a little above 3000, and the C triple bond C will read way higher than that. So it's about 3300 reciprocal centimeter. And you can clearly see examples right here for an octane. So you could see the C single bond C is within the fingerprint region, so it's really useless. But I could base it on having the CH stretch absorbing below 3000. Versus the C double bond C structure, I could see the hydrogen connected to the C double bond C reading above 3000. So you can see it right there, it's 3080 reciprocal centimeter. While the hydrogen is attached to the C single bond C are reading below 3000. In addition to this confirmation, I also have the C double bond C that reads around 1600. So that's the 1642. That is the alkene unit. The C triple bond C, if you have that in a molecule, you should be able to see something that's below 2200, and nothing in that region going to be for other than the C triple bond C. The C triple bond N will be higher than the 2200. So you're not going to be confused between the C triple bond C or the C triple bond N. You could easily tell which one is which. And in addition to the C triple bond C, you also have the hydrogen attached to the C triple bond C. That's usually 3300 or above. So somebody might say, okay, well, I see something right there below 3000. What is that? That's the hydrogen attached to the C single bond C. In the case of symmetry, the C triple bond C will not absorb. Therefore, you're not going to find a peak for the C triple bond C. And since it's an internal alkyne, don't expect a hydrogen attached to a C triple bond C to show up its peak, because there is no hydrogen to start with. That's attached to a C triple bond C. Okay, shifting from hydrocarbons to alcohols and amines. Those bonds usually show up in the very high area, that is 3300 reciprocal centimeter. There is a difference between the two, the OH and the NH. The OH is going to have a broad singlet. So you could see here, this broad peak usually is indicative of OH functional group. Now this OH functional group may be in alcohol or maybe in carboxylic acid. So you're going to see this peak in both carboxylic acids and alcohols. So you will see how it is going to be in carboxylic acid soon enough. In addition to the OH, you will see also the C single bond O. That's around 1100, but it's in the fingerprint region. So that's why we don't look for it. We only look for the OH bond. NH, it's similar in terms of reading, but not the same in terms of shape. The NH will usually show up around the 3300 as a spike. So if it's one NH, we'll see one spike. If it's two NH, you will see two spikes. So here's an example of a single NH bonded structure. And here's another for an NH double bonded. So you can have the two hydrogens attached to that nitrogen are actually causing those two spikes. And that's basically the difference between a primary amine versus a secondary amine. Don't expect a tertiary amine where it's an R3N, where there's no hydrogen attached to a nitrogen, to have a spike. So once again, that's the difference between an amine and an alcohol. Alcohol will have a broad spectrum of that OH stretch, and the amine is going to have a little spike of that NH. If there are two, then you're going to expect to see two spikes. Carbonyl compounds. Now, those compounds that have a carbonyl group could be ketones, aldehydes, carboxylic acids, esters, or amides. So you're going to have to make sure you're able to tell what really that carbonyl belongs to, because the carbonyl on all these compounds, it appears around the same time, which is around the same frequency, which is about 1700. So it's easier to figure out other factors, other readings along with that carbonyl. Now let me start with the easiest one to tell. If you have an ester, carboxylic acid ester, where basically the structure is RC double bond O R, regardless what R group you have in here, you're always going to notice that the carbonyl group absorbance will be the highest, around 1730 or higher. Ketone, aldehyde, carboxylic acid, amide, you're not going to see them above 1735. So the carbonyl will basically be absorbed at the highest of that range, which is once again around 1735 or higher, or even higher. Okay. Now that's the ester. So you're gonna right away, if you see a structure that has a carbonyl reading about 1735, you will tell right away it's an ester. Okay. The next is the amide. The fact that the amide has a carbonyl attached to a nitrogen, that allows for a resonance form. The resonance basically comes from the delocalization of the lone pair on the nitrogen to delocalize to make a double bond CN, making a single bond CO. And that tells you right there that I cannot have an absorbance peak of a C double bond O that matches a C double bond N. Oxygen is more electronegative, so I can tell right away that C double bond O is going to have a difference in polarity compared to the C double bond N. And that's true. Every single time you deal with an amide, you're going to notice that there are two peaks around the 1600. So the 1650 or 16 so range that you're going to have for the carbonyl, the fact that there are two spikes, that tells you right there that I have an amide compound. And obviously there are other factors you could also use to tell if it's an amide. So the amide in this case, it does have two hydrogens attached to the nitrogen, so that tells you that I should have two spikes. So the two spikes belong to the two hydrogens attached to the nitrogen, and the carbonyl is going to have a spike, and the C double bond N, as a result of the resonance form, will have the second spike. So the ester, carbonyl, about 1735 or higher. Amide will have two spikes around the 1725 or 1700 reciprocal centimeter. All right, next, carboxylic acid. Carboxylic acid, you have a C double bond O and you have an OH. So there are two things you're going to notice. You're going to have a carbonyl peak, which is about 1700, and you're going to have an OH peak, which is around 3300. But because of the functional group that's OH in carboxylic acid is going to have hydrogen bonding, it's going to have a very broad singlet of that OH stretch. So that's very indicative of a carboxylic acid. Note, how can I make a difference between alcohol and carboxylic acid? Alcohol is not going to have a peak around 1700. Carboxylic acid is going to have a peak around 1700. So that's the difference between an alcohol and carboxylic acid. Both will have a broad singlet around 3300. Okay, now down to aldehydes and ketones. How can I tell I have an aldehyde? Aldehydes, besides the carbonyl's absorbance around 1700, you're also going to have the two singlets around 2700 and 2800. That those two peaks are actually for the CH part of the carbonyl group. So that aldehyde functional group, which is once again the C double bond O H, the carbonyl is 1700, but the CH is going to read two peaks. One is 2700 and the other one is 2800. The moment I find that along with the carbonyl peak, I know I'm dealing with an aldehyde. If I don't have a carbonyl around 1735 or higher, if I don't find two spikes around 1700, that will be for the amide. If I don't have a carboxylic acid OH broad singlet, if I don't have couple peaks around 2700 and 2800 along with the carbonyl peak, which is 1700 as indicator for an aldehyde, that means I have a ketone structure. Why? Because the ketone has only carbonyl peak that usually shows up around 1700 reciprocal centimeter. All right, carbon nitrogen. So the most important peak that I want to highlight here is the C triple bond N, which is usually in nitriles. That peak usually show up around 2200. If I have an alkyne versus a nitrile, how can I tell the difference? The C triple bond N is more polar, therefore is going to absorb at a higher frequency. And you could see an example here, which is the butyrylnitrile that has a C double bond N, C triple bond N reads around 2250, and those peaks below the 3000 usually belong to the C single bond CH. This is basically a summary of all these bonds, where they usually show up. And as I mentioned, we don't rely on the fingerprint region. We usually try to use the area 1400 all the way to 3500 in order for us to extract what functional group we have. So do not use IR to tell connectivity of a compound, as I could easily give you an alcohol mixed with an alkene, and you can't tell, do I have a compound that has both functional groups, or do I have two compounds being mixed together? So IR does not tell me connectivity. It only tells me functional groups, what functional groups we have. In order for me to figure out whether I have an alkene or an alcohol, I'm going to have to basically run NMR. So that's the tool that we're going to use to tell connectivity. All right, and that will be it for chapter 12.